Alrighty, well, hello everyone, and welcome to this week's DeSci Labs community call. It is November 7th, and the topic of today's community call is quality control systems across industries. So we're going to be talking about quality control systems in manufacturing, in consulting, and in software development, and kind of comparing those to quality control systems such as peer review and validation services in academia. A lot of similarities between them, a lot of differences as well, and some interesting lessons that can be learned from the trade-offs of automation across these industries. So before we dive into the community call itself, as always, I think we're going to give a couple quick updates on this past week for DeSci Labs. So I know that the team has been in Lisbon for a good bit. Philip, I know you were there. Would you mind just giving us a quick update?
Oh, you mean on all the conferences that we've been to?
Yeah, just a high-level summary.
Well, okay. So Chris and Sina and we primarily went to the Code Over Data Summit. So that's the second edition, hosted by Protocol Labs, and it's an amazing community. They had their first summit, I think, in Paris in April or something like that. And this is the first time that we were there, that we were hanging out with everybody. And this is also where we got to know Juan and the entire team. And so now half a year later, they already presented a working demo. They have already built a lot of the things that they were only talking about half a year earlier. So they've executed at lightning speed, and it's really, really exciting to see how this is all coming together. And so I think, like, in terms of the infrastructure, a lot of the things are already working. I think what is probably missing for mass adoption is a user-friendly interface where people actually can use these compute over data facilities easily. So at the moment, this is primarily just for software developers and people that are really familiar with coding. So that would definitely help, having a user interface. And the second thing is they just started thinking about the incentive layer. So how exactly they're going to incentivize the storage providers for actually also providing the computing facilities. So this is really, really early, but given how fast they're executing, I wouldn't be surprised to see all of that more or less fleshed out already in half a year from now. So it was really, really exciting to see that. And the quality of the conference, the quality of the people was just amazing, just really mind blown.
Absolutely. I'm always impressed with Protocol Labs and whatever it is that they do. Huge fan of the Funding the Commons conference and IPFS
Exactly.
Week, Lab Week, Compute Over Data. All of it sounds absolutely incredible.
Yeah.
Then just to close off conference season, which I believe this is our last series of conferences for the year. I was at Web3 ATL in my hometown of Atlanta, where I got to speak to quite a few different Georgia Tech professors and academics on the possibilities of DeSci and on what an open state repository for data can potentially bring to the world of academia. So that was a great conference, definitely a lot of interesting follow-up there. And I'm excited to be working with the team on Web3 ATL 2023. I think that there's a lot more that can be done, and happy to advise there. So with
Cool.
that being said, are there any other updates that we need to go over before we jump in?
I wish Carla would be here. So she actually went to a lot more events during Lab Week than we did. I think she also presented at least one of these occasions. But Sina, is there any update from your end? Something that we forgot to mention?
No, I think that was about all of it.
All right.
Actually, I cannot overemphasize like how hyped we were after this conference. This was just so incredible. We all went home after this like feeling completely empowered, and yeah, it was just great.
That's amazing. I'm sad I couldn't make it. Alrighty. Well, if that's the case, why don't we go ahead and get started on the actual topic of today's community call, quality control systems across industries. So I'll go ahead and get us kicked off. A little bit of my background. I got a manufacturing degree, excuse me, a mechanical engineering degree from Georgia Tech, and pretty much went immediately into manufacturing while I was still in college and out of college. Spent the better part of 3 years there with a focus on quality control. So I did about 2 years in a quality control specific group for automotive parts, went over to headquarters in Stuttgart and did a lot of data analytics for post facto quality control and trying to create feedback loops in the manufacturing process itself. From there, I went into consulting, and just everything in consulting is actually very reminiscent of the way that things work in academia. So some of the quality control systems there will actually pretty closely mirror academia. Philip, who's on the call, has a good bit of experience as a tenured professor in academia, and we'll talk about some of the quality control systems there. And then Sina, who has, I think, the better part of 20 years of experience as a software developer. We'll talk about some of the quality control systems in software development itself. And hopefully between the three of us, we can piece together some interesting comparisons and insights between these 4 different industries. So I'll go ahead and jump off with quality control in manufacturing. So like I mentioned, I used to work in an automotive manufacturing plant and at headquarters doing a lot of data analysis for manufacturing. So one of the things, first and foremost, that you see in manufacturing is that quality control is at the absolute forefront of everything that gets done. And I think a huge reason for that is because the negative impacts of not having quality control are immediate. There is an immediate feedback cycle. If you're creating a fuel injector on a car and your tolerances weren't up to snuff, because that fuel injector has a PSI that is ridiculously high. If something's wrong in the manufacturing process, there's a good chance that it explodes. There's a good chance that that makes headlines, and there's a good chance that those headlines come back to you immediately. So whenever we talked about tolerances in manufacturing, it was on the level of microns. And whenever we talked about quality control, it was almost done with a half reverence, half annoyance kind of mindset from any of the engineers that were there. Because on the one hand, it was put at the absolute forefront of everything that was done. So if you wanted to make a change in any manufacturing process, there was a level of, bureaucracy that was built on top of any of these additions, which was just absolutely absurd. Every single step, to every single part, every single change that you made to the metal of any fuel injector had 3 to 4 different measurements that would happen. And the majority of these quality control systems, at least in the US manufacturing plants I were in, was completely and totally automated right up until the final step where you had a human in the loop. But the amount of checks at each and every individual step was absolutely astronomical. The amount of quality control data that was in place was astronomical. You also had a culture where any given flaw in a part was realistically had been financialized to be estimated at like $1 million. So if you had a customer that returned a part to you, it was going to cost the company $1 million to go back through that parts identifier, figure out which machines it was on, pull all of the records, do a complete investigation, stress testing on the part, and try and figure out who messed up throughout the entire line of supply chain. Because it may not have been a screw up in the manufacturing process itself. It may have been raw material further down the stack. Someone sent you a piece of steel that had inherent flaws in it. And through stress testing, you could figure that out. But that was one of the ultimate responsibilities of the final company who sent said part to the consumer themselves, was going through that in-depth quality control process, and they were held responsible for any mistakes that were further on down the line. And the group that I worked at is one example of this. I think another great group in the space of manufacturing that looks at quality control is Coca-Cola. So one of the big trends that you see in the manufacturing industry at this point is outsourcing. Any and everything that can possibly be outsourced in a company is at this point. At Coca-Cola, 2 of the main functions that are kept in-house as core competencies are marketing and design and quality control. Because a huge part of the value proposition of Coca-Cola is that when you open a can of Coke, you're going to get the exact same pop every single time. It's going to taste the exact same. You're going to have the exact same resistance on the can, the same feeling in your hand, the same color of red. Whenever I say the same color of red, I mean that there are executives in both quality control and design who will keep business cards in their front pocket with the exact color of Coca-Cola red. And about once a quarter, they'll go around to individual plants that are manufacturing Coca-Cola as a contracted entity, and will compare the color red on their business card to the color red on the Coca-Cola can. That is the level of granularity that this gets to. So it's incredible to see a lot of that. But one of the things that's really interesting here is the level of automation. So as I kind of mentioned earlier, everything regarding quality control is automated because you can quantify it, right? I can tell you exactly what the chamfer angle on this specific fuel injector is going to be because I can measure it down to the micron. And I've spent more on the measuring devices than I have on the actual machines that produce the part itself. So that automation is a huge part. And then the customer feedback loops are also a huge part. Where at this point, especially with the emergence of the Internet of Things, a lot of the feedback loops are even automated. So if a fuel injector is in a car, that car has an OBS, which is basically an onboard computing system that will register when something screws up. And as soon as something does screw up, if that car is, I guess, more technologically advanced at this point, an automated report will be sent to the company that manufactured the part itself. So as I was, I guess, up till now, I've talked about a lot of my experience in the manufacturing plant itself. But one of the things that was really interesting to see was kind of the aggregated quality control work that I was doing at headquarters. So at the time I was working there whenever Tableau had first come out. I was the first person in this multi-billion-dollar company to ever get a Tableau license and was immediately given a series of large quality control data sets to try and pull information out of them. One of the things that we eventually figured out was that a lot of sensors in the company had huge problems north of a certain longitude. I believe it's longitude. We looked at a lot of the fuel injectors that came out of Russia at the time, and a part of what we found was, or a lot of these sensors that came out of Russia at the time, and a part of what we found was that the salt from the roads that were used were constantly blocking up the sensors. But this was probably a $10 million project to go out and get the sensors from Russia, bring them in, have them analyzed in a lab, just to figure out that it was salt on the lens. So it was a massive thing, but what you have in manufacturing is both granular quality control. I'm talking 4 sensors per cut on every single part, in a part where there may be hundreds of cuts. And then you have a larger system of, I guess, aggregated analysis post facto that feeds back into any of the individual manufacturing plants, whether that's through IoT automation, whether it's through analysis projects at headquarters, whatever it may be. So whenever I say that there is a certain reverence towards quality control in the manufacturing industry, I really and truly do mean that. And just to tie it all together, the reason is because it's so expensive to mess up. It's news headlines. It is a complete and total loss of customers because there are always competing goods, I suppose. If you don't like Coca-Cola, go to Dr. Pepper, go to Pepsi. May not be exactly what you want, but if it's Pepsi versus a Coke can exploding in my face, those are two different things. Now, thankfully, Coke's never let it get to that point. So that's a look into manufacturing, and I can either pause real quick or go on to consulting. What do you think is best, Philip?
So I knew at some level that they must take quality control serious, but I had no idea that they actually like how incredibly expensive this is and how much priority this takes. So this is very, very different from quality control in academia. We'll come back to that later.
No, I'm serious. In manufacturing, I think you spend more on quality control in terms of dollars spent and opportunity cost of, than you do on the actual production itself. But you have to, because if you don't, you lose customers, you make headlines. It's a serious problem.
Yeah. Makes perfect sense, of course.
And then going from there into consulting. So manufacturing is a very physical industry, something you can touch, you can feel, you can see. There are quantitative numbers. Then you can go into consulting, which is a little bit more, I guess, theoretical work. It tends to be more slides on concepts, going through and talking to people, synthesizing information, giving presentations, things along those lines. The level of quality control in consulting wasn't nearly as heavy. In fact, it was fairly minimal because in a lot of ways, quality control was seen as bureaucracy and waste. Ultimately, what you're measured on isn't specific metrics. It's not like if you give a slide that is somewhat wrong, has one minor flaw, the color is off by just the tiniest little bit, it's not like your whole firm is going to get fired. Ultimately, quality control in consulting is focused a lot more on reputation at the beginning. A lot more similar to academia in this way, where I know that if I hire Deloitte, if I hire McKinsey, BCG, EY, whatever it's going to be, I can pretty much rest assured knowing that I'm going to get a level of information and presentation that I actually paid for, regardless of whether or not that level of information and presentation comes through. Because I'll tell you, being in the middle of it, it doesn't always live up to the reputation that you think it's going to have. So really and truly, the only quality control checks there came from the person who gave the eventual sign off to the client. It was their responsibility to read the deck, to read through the notes and the meeting minutes and synthesize all of it for the eventual client. But half the time, a lot of the people who were on top were so incredibly busy. They had a half dozen, a dozen, 2 dozen clients at once. They didn't really have the time to do this. So quality control, eventually, even in certain projects, was delegated so far down as to be quality control from the person actually doing the work in the first place. So you'd have a grad straight out of college making PowerPoint slides who would send them up to a manager that was working on 7 different projects at once. That manager wouldn't have time, would tell them to double check on their own. It would eventually make its way to the client without having any kind of oversight whatsoever. And the client would look at it and say, what is this? So the level of quality control in that, I guess, more theoretical realm was basically non-existent and based on prestige. I guess the level of post-facto quality control was basically non-existent, which was a huge contrast for me going into the realm of manufacturing. The manufacturing, that post-facto quality control, that was king. That was everything. The customer returned a part, that was $1 million on your head. If a customer returned a slide, that was still billable, technically. So you kind of compare and contrast those two industries. And I think the big difference between the two is whether it was physical work, whether it was a physical, tangible part that someone else could check, or whether it was kind of theoretical work that no one really knew enough to question you on. There was no one who actively could question someone on the slides that you were making, except your bosses who were so busy that they weren't really that invested anyway. So it was just kind of a level of delegated trust. Let me take a pause there. Do you have any thoughts or questions?
It's kind of funny that in the consulting model, you kind of alluded to this, that there's sort of a disincentive to provide high quality because up to a point, right? Because you can always bill more hours. It depends on the terms of the deal.
Yep.
And as long as you can, get a follow-on deal or whatever, you're still good because you can continue to bill.
No, I mean, honestly, that's what it was. It was doing a level of quality to the point where you could build the next portion. It was not going above and beyond. It was trying to find the next bit of money, which, by the way, is a huge part of why I left consulting. It was a very, disheartening industry at times.
Mm-hmm. It's sort of funny. So now that you described how quality control looks like in consulting, I think the parallels between how quality control looks in academia are much closer to consulting than manufacturing, like for sure. So.
But the parallels to software development are likely going to be very close to manufacturing themselves. And ultimately, it's whether or not someone can see the entire back end of your work. But I would love to hear from either the academic perspective or the software perspective, because I think that there is a stark divide that's going to be 2 and 2. At least that was my hypothesis going into this call.
Yeah, Sina, can you maybe say a couple of words about how quality control works in software? That's super interesting, actually.
Yeah, so I'd say I would divide, the realm of quality assurance in software into 2 different categories. So it's going to be mostly one category would be manual testing, the other category would be automated testing. And so and then what you go with is really going to depend on the scale of what you're delivering. So by scale I mean it could be number of engineers, number of features, number of users, and then it would also potentially the number of machines that you're deploying this stuff to, which also kind of scales up the number of users potentially, and then also the speed by which you need to deliver these things. And so depending on the scale and the speed, you're either going to go with mostly manual approach or mostly automated approach or a hybrid. And so to give you a few examples, like a single coder who's knows exactly what they're building, right, and has like a good idea of a product that they want to build and has it in their head, understands it end to end. They can probably get away with a bit of manual testing and just deploy something to users and have that be useful. And then the problems start occurring when you start bringing on other folks that don't have that same mental mapping of what the product should be, or perhaps they haven't written the code that has been already written. So then there's issues that can come with that. So then automated testing certainly helps. But you can even get away with manual testers, right? Depends on the budget and constraints of the organization. So I've seen organizations that do, they say, okay, cool, like we want to move forward delivering new features. We don't want things to break as we go. However, creating automated tests slows us down in some capacities, right? And within automated testing, there's several types of testing. So there's like unit testing, integration testing, end-to-end testing. And so each of these types of testing is going to have a different cost and a different in terms of like feature development. So, I think a basic one is unit testing is like tends to be lower cost, easier for the folks that are working on a new, let's say a library or module. They can test that module individually and it's isolated, doesn't touch a lot of other parts of the software. But then if you start working with like a database or an external resource, then you want to start doing potentially integration testing. But the thing is that can start slowing things down. What if your database schema changes over time? Writing an integration test for a database schema that changes, it could be a little tougher. Also the actual speed by which the tests run can slow down if you're relying on an external resource. So, in general, the ideal best practice for like a large software development company, it's probably going to be automate as much as you can. And for a larger company, that makes sense because your product is more well defined, usually, right? So yeah, there's different setups, right? And then overall, in general, for me, I want to automate as much as I can and maximize the amount of automation, but then minimize the amount of refactoring that needs to occur as a result of changes. So if you have to do a major change and that requires you to like go in and rewrite all your tests or completely change things around, that can cost time. And a stopgap for that is to deploy manual testers. So if you're doing a big, huge change that requires you to redo your entire automation suite, well, but you still need to ship the feature. Well, we can bring on a few manual QA testers to go in and make sure everything works as expected, and then take some time outside of the release cycle to rewrite that test suite to make sure that as the product becomes more well defined, that you can make sure that the product continues to do what it's supposed to do. And a part of it too is like in software development, it's not always clear what the product should look like. You could have several different kind of like iteration releases where the product changes quite a bit, and as there's a lot of turbulence in the product development, like we're changing UI features, we're changing backend features, we're changing how the product works. Those may be good moments to deploy manual testing, and then as the product becomes more mature, more stable, then you deploy automated testing to make sure that maybe you're scaling the team, maybe you're bringing in new engineers that don't know how the product's supposed to work. Well, it becomes it starts making it a bit more resistant to breaking. As you bring in folks that may have less information about the product, then you're putting out on guardrails for them. So I don't know. I feel like I've been going around this several different made up scenarios that may be confusing to follow. But in general, we found that there's been different attempts at how to do software development and software engineering. We've had this like kind of design waterfall iterative model, and then we've had the agile iterative model. There's been, and so I think in general, the smaller you make your iteration cycles, it tends to produce a better product. If you have a long design cycle and then a long development cycle, it ends up causing you to basically be developing a product in a vacuum, which basically increases the amount of time before you can catch that and then change what you're doing. Shorter development cycles where stakeholders are involved with and testing the product as it's being built. You can catch issues earlier, and then as the product stabilizes, deploy automated testing to make sure things don't break in the future. But yeah, I think I'll pause there and for any comment or question.
Yeah, I've got quite a few. Well, first off, I think it's really interesting to see how quality assurance in software development seems to be on a scale based on need. And that is absolutely fantastic to hear. And I guess I went into this conversation thinking of software development as more of a tangible development task. But one of the things that you kind of hit on as you were talking was the fact that oftentimes you don't know what the product is going to end up looking like. So that makes quality control significantly more difficult than in, let's say, manufacturing, where I know that I want to produce the same exact car part every single time and can basically build processes that define what that car part should look like. Whereas in consulting, it really was different every single time. So I don't always know what it's going to look like. And I think that that's an interesting parallel to academia because maybe, Philip, you could jump in here. The moment you start a project, you don't know what the outcome is going to be.
I will say something here about, different sizes of companies and different, as products become more mature. Like at a startup, when the product is not really super mature, right? There's like less of a, it's tougher to allocate resources to measuring and optimizing and doing these sorts of tasks, especially as you have less user scale, your product is changing. It makes less sense to allocate resources to quality assurance and measuring app performance and all these sorts of things. than it does just to get folks that are just building and designing, right? Then if you look at something like Google with their Google search, it's a fairly stable product, right? People know what they want out of the search. They want it to be fast and they want it to have relevant results. And these things are, you can try and you get signals from users, that allow you to, sort of measure and create proxies for, is this loading fast? Are users having an experience, or are they finding what they're looking for? You can then it becomes its own engineering task to turn these signals into useful information, and then try and feed that back into the whole process of like indexing the data and like delivering that to users. So I just wanted to make that distinction.
No, that's a valid distinction to make, and thank you. And I think it's interesting to think about each individual piece of research in academia as its own little startup, because that's essentially what it is. But it's startups on an industrial scale. So you do have to think about some of these, I guess, larger aspects of standardization and process, similar to what you would have for Google. I guess the one main difference between software and manufacturing, or one of them, is the rate by which you can get feedback. So like I kind of mentioned in manufacturing, if I wanted to look at a part, I had to wait for it to go drive around for a year in Russia and then take 6 months to actually go get the part back itself. So it's a year and a half, sometimes as low as 6 months feedback loop, whereas in software development, it can be a span of weeks, days even. So it's a huge difference. But yeah, no, that's fascinating. Okay.
Super interesting. So, hearing what software quality control looks like, I think this is very, very different in academia. I think that the closest analog that we heard so far is really consulting. So, I think quality control in academia probably has like two parts. There is an unofficial part and there is an official part. So the unofficial part is simply how the academic community is going to react to a particular piece of work that scientists put out there. And traditionally, science has largely relied on this, sort of unofficial or intangible part that is difficult to measure. But the idea is very simply that if scientists publish something that just doesn't make sense or is false, that others will point this out and the error will be self-correcting as the literature progresses. Now, the official part is, of course, peer review. And peer review is actually really surprisingly to most academics nowadays is a relatively recent development. So peer review actually wasn't a thing until the 1970s or something like that. And it originated out of a demand of Congress to have more transparency about how money is being spent on science and what happened to it down the road. And there was a really funny incident that happened, like I think in the 1920s or something like that, when Einstein actually sent a paper on gravitational waves to a journal. And the editor did something that Einstein didn't see coming. He actually sent it out to referees, and the referees had comments, something that nowadays would be like completely the norm, right? But back in the days, Einstein was completely outraged about this. And I'm just going to read this out from you. So he wrote a letter back to the editor in question, and he said, "We, Mr. Rosen and I, had sent you our manuscript for publication and had not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case, erroneous comments of your anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere." So that was Albert Einstein. And then, of course, peer review actually started to become a thing in the 1970s. And it is now completely standard that basically any type of academic publication first goes through some type of peer review process. And, well, so it's actually, to some extent, it is debatable whether the introduction of this formal type of quality control has really increased the overall quality of the academic literature. I don't know if it has. I don't know if anybody has studied it. but it's pretty clear that, if you just look at the quality of papers that is coming out nowadays, that there is a vast majority of papers that are either not terribly relevant, or they have flaws that were not spotted during the peer review process, and often also not even afterwards in the post-publication process. So there is, of course, the replication crisis that we talked about quite a bit, and within this topic of the replication crisis, we also had seminars actually on the Future of Seminars series where Giddy talked about examples of work that got published after peer review in really high impact journals, and that created a lot of follow-up literature, a lot of scientists that build on the original study results, which then a decade later or so turned out to be false. So there was this. That was actually not only one occasion. There was like a lot of these examples where an original study that got published after peer review in a top journal then later turned out to be false or non-replicable. And a lot of money has been wasted on conducting follow-up research that built on those wrong findings. So I think that the short version is that quality control definitely leaves something to be desired in academia. And we can talk about why that is the case and how we can possibly solve that. But maybe just one remark on why peer review emerged. I think a part of it is that originally editors of scientific journals, they literally engaged with each paper that was submitted to their journal. So the editor was the ultimate authority that made a decision about whether an article was published or not. And the editors, of course, they needed to have time to engage with the work that was submitted, and they needed to be experts in the field. And that worked for a pretty long time, pretty much without anybody really questioning the system. But then a lot of things changed in the 1970s and 1980s. One of them is that we all of a sudden saw an almost exponential increase in the number of publications that people were submitting. So there was just so much more content all of a sudden being thrown out there that editors were just really in a position where they could not possibly read each paper all by themselves and make that decision all by themselves, right? So part of why peer review started to become a thing is because editors needed a way to actually outsource some of their work to others and actually just basically get help in evaluating these manuscripts. And I think that was also part of a larger trend in academia, which also started in the 1970s and 1980s, where basically governments and those that were giving money to science were requesting more accountability, and were also requesting more measures, quantitative measures of research productivity, right? So all of a sudden, incentive mechanisms have been created for scientists that are steered at producing a high number of publications, and ideally a high number of publications in top journals with a high impact factor, right? And that's not necessarily a bad thing, but it definitely also created a lot of problems along the way that the peer review system itself could not solve and still isn't able to solve.
I would argue that at least for computational work, integrating some software development practice of having ability to click a button and run a test suite, and just to verify stuff like, oh yeah, all these charts match. It's a huge it's a huge productivity boost for these editors, right?
Exactly. I mean, the idea is so powerful if you would actually enable self-reproducible manuscripts where the editor or referee or basically anybody can come in and just verify that the results that the authors are claiming in their manuscripts are actually derived from a particular piece of code, which they can audit, and an underlying data set, which is in the open domain. And if you run the code on that data, you get the results that the authors were claiming. So this is a level of excellence that you would think should be the standard, but it's completely unheard of in academia. It's only a very, very few exceptions where this is actually the case. So one example where they're actually trying to do that, and where they basically implemented that for a couple of years now, is the American Economic Association, where their top journals have a data editor who has the job of literally making sure that all the accepted manuscripts do not only make their data openly available, but they also have an editorial team that checks the code. So they ask the authors to submit the code and to document the code so that anybody can understand what the code is actually doing. And then they check the code and they run it on the data to verify that the results in the paper match those that come out of the data and the code. But this is extremely labor intensive, and it's the complete exception. But it definitely led to a situation where the empirical work that gets published in these journals in economics are arguably of a much, much higher quality than those in many, many other fields, including journals that have much, much higher impact factors.
And my tendency initially was to think that this problem would be a little bit better in the fields of computer science, but I'm not sure if it is or not. I don't have too much experience in like doing research broadly on the meta science here, but I'd say off of my own kind of I was looking into commercializing what's called blind watermarking on images. And so what this is it's a technique you can do with digital signal processing or other techniques where you embed a watermark into an image and make it machine readable, but not really apparent to a human. And when I was researching this to try and commercialize it, or an aspect of it, for one of my projects I was working on, I basically ran into I went on GitHub and searched okay, blind watermark, right? And then I found dozens of repositories, right? And then inside of those repositories, I was realizing that all of them had linked to some paper. So a lot of these were academic, kind of test repos for in academia. And then also I would search in Google, blind watermarking, I'd get a bunch of papers, right? And then no code, or maybe some of them had code, right? And as I was, so basically I ended up with I don't know, half a dozen, or a dozen or two repos, papers, varying levels of code completion, varying levels of description in the paper about what what's happening, and so I would go around, and basically it was I probably looked at at least 20 repos, okay, and then basically I remember just damn, it's not standardized at all, right? There is no ubiquitous standard to use a container, right? Or have any of this stuff be easy to run. It's like if you find that one diamond in the rough, it's you're in huge luck. So I just remember this personal kind of anecdote of mine, and I was surprised, but I also wonder. It makes me wonder: are there certain journals or communities in computation science or computer science? I'm wondering that these communities that you mentioned, the American Economic Association, but I wonder if there's other communities that enforce these standards, and if there are, we should absolutely find them.
Yeah. So what I've seen in human genetics is that a lot of people that are doing computational work in human genetics, or that are actually developing methods, there is a pretty strong ethos now in those communities for open science practices, and part of it is that if you develop a new method, that you make the code openly available, right? So the mathematical derivations are in the paper; they can be checked by the referees, and then the code is in the open domain, and then basically anybody can come in and actually check the code. That is super, super powerful. And but I think it's still a relatively small minority of people that are doing that. So even if you look in computational genomics at those people that are primarily using these methods rather than developing, you can immediately see that there is a drop in the level of efforts that they're making in terms of making their results and methods and all of that completely open, right? So there's a lot of stuff where, you know, people are, of course, they're programming, but very often they're not making their entire analytical pipeline openly available. It's rather that they wrote a piece of code and they ran it and they wrote down the results, and then, you know, the code may have gotten lost, or it's not very well documented, and you have libraries of like 30 or 40 different versions of the same type of code, and you don't know which one they actually ran for the paper. And it gets really, really messy very, very quickly.
I mean, these seem like easy standards to implement. Well, easy is a strong word because it's more of a cultural aspect, but it seems like standards that are implementable in practice. Seems like these are things that can be done.
They can be done. I completely agree, and it's also, like you said, I mean, it's partly cultural, right? So if you know, if PhD students learn from their supervisors that the only thing that counts is to just get a paper out in a high impact journal, and nobody's going to ask you exactly how you did that, then don't be surprised if you end up with a new generation of scientists that are really, really good at publishing a lot of stuff that are not reproducible and not replicable. But if you have, you know, if you basically have professors that are training the PhD students in coding methods and also documenting all of the steps along the way, and sort of like implementing this ethos of, you know, quality first and openness first, then you probably end up with much more positive results. But that's not really what most academic institutions actually incentivize. The rewards for doing that, for going the extra mile, are pretty low, if non-existent in most cases.
So another part of quality control in academia that I don't know that we've touched on to this point is the concept of a retraction. And in, I guess, all of the other industries that we've talked about to this point, there is something that comes down 6 months, a year, 2 years later, which is a massive financial burden that is essentially the stick accompanying the carrot of, you know, user adoption or scientific knowledge, whatever it may be, where if you get something wrong in manufacturing, it's $1 million for that one single part. In software development, it can be an exploit that takes out $500 million of liquidity, whatever it actually is. And there is a certain amount of personal liability on both. And I think retraction is probably the most closely aligned concept to this nuclear fallout option of everything eventually went wrong. I would consider that a part of QC.
Yeah, totally. And I mean, so retractions are definitely a thing in academia. They happen very, very rarely. But if they do, they're a huge embarrassment for the authors, right? So that's the ultimate form of public shaming, where, you know, you basically have to retract your work and everybody is going to look at you and say like, oh my God, they really fucked up, right? So it happens really, really rarely, but it is a pretty powerful thing if it does happen. There's also a lot of journals, they have this option to publish corrections. And so we actually had a number of papers where just formal things ended up being wrong, right? So I remember vividly this one case. We had a paper in Nature Genetics that was a result of a very large research consortium that pooled data from I think over 70 different research centers from around the globe, and that had over 200 co-authors. And we managed to forget one of the groups that contributed data as authors on the paper. And when the paper came out, the PI of that group called me and was basically yelling at me like for 15 minutes. I think like I easily lost like 2 inches of my body height. I was so incredibly embarrassed. I was like, oh my God, how is it possible? We really fucked this up. The paper was great. The paper was like, it was extremely well cited and very robust, and it had discovery and replication, everything together. So scientifically, the paper was great, but we literally managed to just forget 5 out of 250 co-authors. So we had to publish a correction that just, that added these additional co-authors. And then, of course, oh my God, this embarrassment will never go away. So I think I've been bruised by that eternally.
Oh, no. But that's such an easy mistake to make. Oh, that's the worst.
It is. Yeah, exactly. And it's often stuff like that where, it's a formality, is something like in the acknowledgements, somebody forgot to mention a grant, or, you got the affiliation wrong, or you misspelled an author name and stuff like that, then often leads to these corrections. So these are sort of like the benign.
Yeah, that would be considered a formal retraction, just forgetting to write someone's name on the paper. You would have to have an actual retraction for that.
Not a retraction, but a correction, where basically there is like a one-pager being published in one of the later issues of the journal that says correction for this and this article, and then you publish the correction, then you say what needs to be corrected, and that's it. But it's still embarrassing.
Yeah.
I wonder why that's embarrassing. Is it
right?
just the speed of publication that causes these sorts of things to be shameful? Because if, it's like in a GitHub repo, right? Or, if I miss something, fairly small, do a typo, we can do a commit and not feel too much shame. And we it can suck if it goes out to production, right? That can be embarrassing. But these things tend to be, resolved relatively quickly at least on the software engineering side. It can suck if like users, get locked out of their accounts. That can be, ridiculously embarrassing. But in this case, it doesn't seem like any economic harm was done. Right.
Yeah. No, it's true. I mean, so the harm that was done in our case was sort of we were just not careful enough to really double check everything. And it was a paper that was like 5 pages long and had 200 pages of supplementary materials, and like literally hundreds of people contributing. And it was like, I'm not trying to make excuses. It was just really, really difficult to make sure that absolutely nothing went wrong. But in that particular case, it was like, okay, we should have double checked that, and not listing an entire group of people from one institution could have also been something that, they could have thought we did that on purpose. Of course, I made it very, very clear that it was not on purpose, but it was still really embarrassing to have to admit that this happened and that it was obviously a mistake and that we're going to fix it. So I don't know. It was more like soft reputation. Yes.
That level of perfectionism, though, just feels so wildly detrimental to progress. I mean, coming out of a realm that's more technical and emerging tech related, I know I talked more about manufacturing. It's try fast, fail fast. It's constant things happening, and the incentive is to ship every single day, if at all possible. If you make a mistake, you go back in and change it tomorrow. If it was years of humiliation for just forgetting one single name, not commenting on a piece of code or whatever it may be, that leads to cultural issues on such a massive scale. Because there almost seems like there would be a fear of publishing at this point. You're going to quadruple check, and it's going to take you 2 months to actually go through that instead of pushing code every single day.
Oh, yeah. I mean, that is so true. I mean, there's the amount of like quality control that we implemented at the project level, where we especially in the early days when, what we were doing was really novel. Nobody had done it before. And the results that we were reporting were completely misaligned with earlier, publications. So they were really like, we needed to make sure that like literally every single thing was like absolutely perfect. And I don't even remember like how much time we spent on formalities just such as checking that we actually have all the authors correctly listed, and that the affiliations are formatted the right way, and all this crap. Like, enormous amounts of time were wasted for that. And it's sort of like in academia, you always have these two conflicting incentives. On the one hand, yes, we're incentivized to basically publish like machines, and ideally only in high impact journals. So you're rewarded for quantity and impact. But on the other hand, if you do fuck something up, it's it's very, very painful.
It seems like the most effective methods of quality control that we can identify are those that are immediately automated or automatable or standardized to the point where people don't even have to think about it. And I would love to see, because this seems like such a simple mistake to fix. If this paper was written with actual intellectual provenance, a trail of intellectual provenance that kind of was able to connect code and data to the final paper, you don't have to worry about who you're writing on that final paper, what names are on there. They're just automatically on there because they contributed to the piece of knowledge.
Yeah. I mean, it's one of the many reasons why I really am a huge fan of this concept of dynamic research objects. So we move away from the static PDF that is sort of the version of record that cannot possibly be changed or fixed in any way, but towards a research object that literally lives along with the research project, that begins really early on, maybe with an analysis plan, and then some first data and some code and the first version of the manuscript, an updated version of the manuscript, and then a published version of the manuscript. But even after the official publication, I love the idea that, with the research object, you can still go in and you can still easily fix things, and you can add things, you can still improve things, and you can still build upon them. That's one of the many reasons why I really, really like this idea.
No, it's absolutely incredible. And I think we're at 12:59 right now. So why don't we go ahead and just give a quick second for final remarks. This has been a wonderful community call. I've really enjoyed it. Alrighty. Well, seeing no final remarks or questions, I think I'm going to go ahead and sign us off for the day. Thanks, everyone, for joining. This has been a lot of fun.
Thanks, Eric.
Alrighty. I'll talk to y'all later.
Okay. Ciao.